mRNA. And the reason it's got these stems and loops is it's just trying to remind you that mRNA has secondary structure. It can pair on itself. It may make a structure much more complicated than this. But this is just to remind us that the RNA does have secondary structure. The M7V is the cap at the 5' end. It's a modified V nucleotide. And then the poly A tail at the 3' end. Okay? So we got this by doing mRNA enrichment. Then we fragmented the RNA with heat. So this indicates that this mRNA was broken into 3 fragments. And then we hybridized with random primers. And the random primers hybridize 5' at this end and 3' at this end. They have to be anti-parallel. So we would copy this fragment going 5 to 3 this way. And this one 5 to 3 that way. And this one 5 to 3 that way, right? So these two are short and it's hard to see in the diagram, but this one, pretty clear. If the random primer hybridizes here, we're going to get this nice cDNA. So that would be first strand cDNA, right? And the first strand cDNA then is down here. This is confusing, and I'm going to get you to flip your brains around here. So our RNA is in red, and the cDNA synthesized off of the random primers is going to be in gray. So this is 5' to 3' in this direction. Now, because of what's going to happen later on in the protocol, in the diagram, we're going to flip that around this way. So just take this sequence here, and we're going to copy the first strand cDNA in that direction, 5 to 3. So this will be the 5' end, that'll be the 3' end. And now we're just going to turn the whole thing around in space. So we're just going to rotate it this way, okay? And if we rotate it that way, then the 5' end with our ends is now over here. Here's our cDNA, 5' to 3' that way. Now, why did they do it in the figure? It's because the focus is on our cDNA, our first strand cDNA, and you should always draw your sequence focus in the 5' to 3' direction. So NEB is following the rules here. So they flipped it around this way, so now our first strand cDNA, starting with the random primers, is 5' to 3' left to right. Everybody clear on that? I did not do this on the board because I didn't want to confuse you at the time. Okay. The red sequence here is our RNA, remember? This is our first strand cDNA that started with the random primer. 5' to 3'. That was first strand cDNA synthesis. Then we did second strand synthesis by nicking the RNA and replacing it with DNA. And this is showing us that we've got our ends that are not blunt. Don't worry about how that happens. Right? So don't worry about the details here. They're just trying to show you that your double-stranded cDNA that you generated using the RNase H and the DNA pol 1 is not blunt. The other thing they're not showing is the nicks in the second strand cDNA here, but you know they're there from our previous discussion, right? So here we have a double-stranded cDNA that's not blunt, and remember that the T4 polynucleotide kinase has to come in and phosphorylate this 5' end, right? Phosphorylate the 5' end, and we get the nicking of the RNA and replacement with DNA. And then in the end repair, again, we add the phosphate group, and now what we can do is to fill in with the T4 DNA polymerase the 3' end here and the 3' end here. They're not showing a 3' overhang, which is a little annoying because 3' overhang is the one that we always get, and I showed that on the board there. So I would say that the way that I draw things on the board is more detailed. These things are a little bit more like sketches of what's going on. So anyway, the ends get repaired. So we did a cleanup, and we did an end repair, and now we've got blunt-ended double-stranded cDNA. Okay? Using the T4 polynucleotide kinase, we also added a phosphate group here. So now we have double-stranded cDNA with blunt ends on both sides, and the phosphate group where our random primer was. So we had the phosphorylation. In addition to that, we had the Taq polymerase, which added an extra A to each 3' end, an extra A to each 3' end. So there we go. There's the A overhang, single A nucleotide on each end. They call it DA tailing, but boy, that's a pretty short tail. Single A. Okay? Not much of a tail, but it's a little one. So this is where you're at now. This is where you got up to. So you've covered, the first 2 pages here of this diagram. You get up to the point where we now have double-stranded cDNA with a single A overhang on each side. Everybody feel comfortable with those steps? Good. There was some discussion at the end of last lecture where people were teaching each other what was going on. That's always great. You guys should all sit at lunchtime together and go over this and make sure you've got it all worked out. No chit chat. Gotta be ready for that final exam that's coming on. All right, so we have double-stranded cDNA now with the A overhangs on each side. Now what are we going to do? Oh boy, this is where things get really exciting. You thought it's been good so far, just wait. Now we're going to ligate on adapters. Holy Toledo. What's going on here? The adapters are actually single-stranded DNA. The 5' end of the adapter has a T, and that T will hybridize to that A, the A overhang. And then it loops around and it connects at the other end with its 3' end at this end. So the way the adapter ligates on, this part of the adapter hybridizes with itself, so it makes a stem. This part does not hybridize with itself, so it makes a loop. We also hybridize it at this end. Same thing, the T hybridizes to that A, and so we have this adapter now going around and ligating in that direction. Same adapter on both sides. Same adapter. This adapter is a DNA molecule, but strangely enough, it has a U in the middle of it. Now, U doesn't belong in DNA, does it? DNA is supposed to have G, A, T, and C, not U. This U is put in artificially in the synthesis of this adapter. This adapter is really a big, long oligonucleotide. I think it's about, I have to look this up, I think it's about 80 nucleotides long, 70 to 80 nucleotides long. Has a U in the middle of it. That U is a deoxy U, so it's a DNA U. That's a really unusual nucleotide. That is not a normal nucleotide. So this U is here, and it doesn't belong there, because U's are not supposed to exist in DNA. Because U's aren't supposed to exist in DNA, there is an enzyme that is designed to cleave out those U's, and so we're going to end up breaking our adapter with this enzyme that's called user. And I'm going to take you through this again after lunch when we are actually doing the protocol. Now, why are we doing this? This adapter, ligated onto both ends, has essentially converted our double-stranded cDNA into a single-stranded molecule, right? You crack it around, it's all connected. It's really a big, long, double-stranded, big, long, single-stranded DNA molecule, right? To convert it back to a double-stranded DNA molecule, we need to clip the ends here, and so we'll do that. Now, why make this stem loop thing just to break it later? Well, if you ligate it on this way, you only need to ligate on one thing, and we're ligating the same thing on both sides, and then we clip it, and now we've got adapter sequences on both ends of our molecule. So it's really clever. You just ligate on one thing, and then you've got your two different ends of the molecule. The green sequence and the yellow sequence are not the same. So we have two different adapter sequences on both ends of the molecule, but we only had to do one ligation to do it, right? So very clever system here. So now we have two different sequences at the end of the molecule. They're not paired here in the figure because the green and the yellow don't match. They're not complementary. Okay, they're complementary over this little part here, so that part actually does hybridize, and it's not very clear in the figure. But the beginning part of the green and yellow does hybridize, but then after that it does not. And so that's why we get these tails icons. Okay? Don't worry, I'm going to do this again. This is the first time through, just to show you where we're going. Then we're going to have to, after this, we're going to have to do a size selection because we have to get rid of the excess primers that we don't want. So we put a lot of primer in to force this reaction to make sure that we got these primers ligated onto both sides. We call them primers or oligonucleotides or adapters, whatever you want to call them. We wanted to make sure that we got both sides with the adapters, so we put in a lot of adapters. And so we have to get rid of those, and so we're going to do another size selection here with answer B, similar to what we did before.
Question.
Yes.
Sorry, this is maybe 5 minutes delayed, but you called it a ligation, you said no to one ligation, but I thought it was actually A hybridizing to a T on this adapter molecule.
If we're going to count that way, it's actually 4 ligations, because we have to ligate here, we have to ligate there, we have to ligate here, and we have to ligate there, right? So it's 4 ligation events, but it's only one reaction we have to run. We only have to run one reaction with one molecule added, and that's this one adapter. And that's going to generate then for us 2 separate ends. If we were going to do it by just ligating the green one and the yellow one on, it would be complicated because we'd have to run those reactions separately, and it would be more complicated than trying to do it the way with 2 ligations. So by 2, I mean 2 separate ligation runs. You want to think about it that way. So here we put in one thing, and we do one ligation and one tube. If we were going to add these separately, we'd have to do 2 separate ligations. Okay? I know this is not the easiest thing in the world, which is why we're going to do it again when we actually do the protocol. Right?
What is the user?
The user is the name of the enzyme that's going to cleave at the use, and I'm going to take you through how that works in detail and why it's called user. It's actually a mix of 2 different enzymes.
So there is a pairing part after the A, or after the
Remember, we added the A nucleotide with the Taq polymerase, right? So when we added the adapter, there's a T on the end of this adapter that can ligate to the A, and then the 3' end will ligate over here.
No, but the adapter also pairs.
That was my confusion.
Oh, this part here?
Yes.
Oh, that's the 5' end of the adapter is homologous to the 3' end of the adapter. So they will actually hybridize like this and form the stem loop. And when it ligates on, it's already in this stem loop configuration. So the T will ligate here, and the 3 is already in the correct position to ligate here.
So it's a base pairing or ligation or both?
No, this is base pairing here. The stem is formed by base pairing within the single-stranded adapter. The single-stranded adapter is 5' and 3' ends can pair together. This part does not pair because it's not complementary, and so it makes a loop. But this part is paired. I think in the actual adapter, it's about 8 nucleotides to this pair, but I'd have to look it up.
And when the U is excised, they don't pair in within the adapter.
No, when the U is excised, this part will make you know, the straight line, and this part will make the straight line. This part will still be hybridized.
Oh, those would be fine.
Still be hybridized. Same thing at this end. And so in the figure, it's not clear, but the beginning of the green and yellow here would still be hybridized on both sides. Okay? Those of you at NED, you can hire me as a consultant to make your figures a little more accurate. It's not bad. It's not bad, but it's not perfect. Okay? We're going to cut with user, and then we're going to end up with two different molecules on each end, but the 5' end here and the 5' end here have the same sequence, 3' end here and 3' end here have the same sequence. And again, that's because the adapters ligated to both sides. It's the same adapter on both sides. But 5' have to ligate to 3', right? And so it goes on one way on one side, and it's flipped over on the other side. So this is what I want you to do for lunch. I want you to diagram this kind of thing, and I want you to convince yourself that the adapter ligates on with the green on the bottom here and the yellow on top here, but with the green on top here and the yellow on the bottom here. It has to go that way. It's the only way that works, right? Because you have to ligate a 5' phosphate to a 3' hydroxyl. So on our original cDNA, this is the 5' going to 3' here. So this is the 3' end of the cDNA. It's actually the 5' end of the adapter that's ligating on here, right? 5' end of the adapter that's ligating on here. And that's why when we cut with user, this is 3' end. So this one is going to be 5' to 3' this way like it's supposed to, 5' to 3' this way like it's supposed to. The only way to convince yourself of that is to draw it. I can use my mouth to say it over and over and over again, but to really convince yourself, you really want to draw it out. And remember that you have to ligate a 5' end to a 3' end. 5' phosphate to a 3' hydroxyl. And if you remember that your cDNA is 5' to 3' this way and 5 to 3 that way, this is the only way that your adapters can ligate on. The only way. They go on this way and no other way. Okay? And that's important so that after we cleave with user, we have this arrangement here. Okay? After we do that, we're going to do another size selection. I'm hesitating on whether I want to go any further. Let's just see where we go. We're going to do another size selection and another buffer purification. That's really the main thing here. We're going to do a ligation, and then we have to change the buffer to do PCR. But then we're going to PCR amplify this, and this is called amplifying our library. So we've got all these cDNAs, right, that we've cut into pieces. We've got small cDNA fragments. We've ligated on adapters. Now what we have to do is make more of these in order to do sequencing. We need more copies. So we're going to do what's called a PCR enrichment. And to do the PCR enrichment, we're going to hybridize primers to these tails. And then things get really crazy. So if you scroll down, you're like, this is really bad. And it is. It's scary. So that's why we're not going to do that now. We're going to get you through this scary part first, and then we'll do the other scary part later. Okay? One scary thing at a time. All right. So that's really all I want to tell you about where we're going with the cDNA. That's where you've been and where you're going. So again, we've done this end repair, and we've added the x-rays. That's happening right now. And the next thing we're going to do is this adapter ligation. And when we do that, after lunch, I'm going to draw it on the board. So double-stranded cDNA is gray. We made that in the previous few steps. Your double-stranded cDNA is blunt here, except we added an A on the 3' end. So it's got a 1A overhang. This is your cDNA. The cDNA has the single A overhang at the 3' end. Same over here. It was blunt, But then we added that A, and so now there's a single A here. So each 3' end has a single A. So the 5' and 3' here indicates the 5' end of our CDNA here, and the 3' end here, the 5' end of our CDNA here, and the 3'. Okay? Very good. Now we add this single-stranded adapter, but the single-stranded adapter is in this configuration because it can pair with itself here, and that's what's called a hairpin. And so, because of this hydrogen bonding here, the adapter will look like this actually. And what happens is when we add the adapter end ligase to the reaction, because of this single T that's sticking out, so the adapter, when it hybridizes like this, it has a single T sticking out. And a single T sticking out here. That single T will hybridize to that single A, and we'll get a ligation right here. Right? We'll get a ligation in this thing here. And this is actually the 3' end. I know that the 5' and 3' was confusing here. This is for the cDNA. That's the 5' end of the cDNA. This would be the 3' end of the adapter. So the T overhang is a single 3' overhang on the adapter. So that's the 3' end of the adapter there, and the 5' end of the cDNA right there. Okay? And that'll be the first thing to ligate because this hydrogen bonding is going to enable that ligation to occur very quickly. Now on the other side, this is the 5' end of the adapter ligating to the 3' end of the cDNA, and that'll lock into place and also be connected by the ligase enzyme. And so now we'll have our adapter ligated on that. Is that clear to everybody? Exact same thing on this side, except it's the mirror image, right? This is the 5' end of our cDNA, the 3' end of our cDNA. This would be the 5' end of our adapter. The 5' end of the adapter will ligate to the 3' end of our cDNA, and the 5' end of our cDNA here will ligate to the 3' end of our adapter. So the same thing happening on both sides, just a mirror image because of the way the 5' and 3' work out. It's easy to remember how this thing is going to go on if you remember that a 5' end has to ligate to a 3' end. You got to have a 5' phosphate and a 3' hydroxyl for ligation to occur. Okay, we're all good with this? Yeah. Good. The adapter, remember, has this U in the middle of it that doesn't belong there. Now we add this user enzyme, and one of the enzymes is that UDG enzyme. And what the UDG does is flip out the U. Now the U looks like it's in the backbone here, but you know that's not really what it looks like, right? Here's our DNA backbone in the loop. So this is part of that loop I'm showing here. And the backbone is alternating sugar phosphate. You know that from the DNA models that I showed you on day 2. So there's sugar here, and the sugar has the base attached to it. The base is going to be U sticking inside like that, right? So it's going to be sugar phosphate base, sugar phosphate base, sugar phosphate base, but the bases are sticking in off the sugar. So we'll have phosphate, sugar, phosphate, sugar, phosphate, sugar. This sugar has a U on it. And what the UDG enzyme does is to simply clip off that U. So it clips the bond between the U and the base, and remember, between the U and the sugar, and remember it's connected to the 1' carbon of the sugar. So it's clipping the U off of the 1' carbon of the deoxyribose sugar. You guys want me to show DNA? Show DNA again for one? No? Yeah. So I can do that really fast.
How many years do you have?
Just one. Just one U.
It is using the base only, right?
Yes. Let me show you on a DNA diagram. We have phosphate, sugar, sugar, phosphate, sugar, that's the backbone. So this is the backbone of the molecule here, sugar, phosphate, phosphate, sugar, phosphate, sugar, phosphate, sugar. And then base sticks out this direction, and it's connected at the 1' carbon here. So the base is always connected to the 1' carbon on the deoxyribose sugar. And what we're doing is clipping off the U by clipping this bond right here. So U is a single ring of C, clipping right there, and that clips the base out. So the sugar phosphate backbone is still intact, but the U's been clipped out. And that's what the UDG enzyme does. Well, now what we're going to have is we're going to have a sugar sitting here without a base on it. Right, so just imagine this base gone. We're going to have a sugar with no base. And the endo-4 enzyme recognizes that that's not correct. And it thinks what it's supposed to do, because biologically that's what it does. What it's supposed to do when it sees no base there is to clip at the phosphodiester backbone. And so what happens then is that after that cut is made, the endo-4 comes in and cuts the backbone. And it cuts it right at this position here. So if you eliminate this base, you're going to cut the backbone here. And now your two ends are now linear instead of a hairpin. Right? Does that make sense to everybody? Okay. Go back to the other diagram and how to So in the next period, you're doing the adaptive ligation and the user, so that's as far as you're going to go in the next period. And the next thing you're going to do after this is the PCR enrichment, and things get a little interesting here. You can see things look complicated than they are. But I'll save that for next time. I want to do the sort of step-by-step so you're not overwhelmed with all the weirdness all at once, right? Yes, Brian?
When you get precise phospho sugar like this, does that phosphate group go with like the 5' carbon?
So once you make that cut, you're going to have the cut made in the phosphodiester bond. So when the cut's made, you'll generate a 5' end with phosphate and a 3' end with hydroxide. It'll be a normal cut, just like what restriction is. Right? Yeah.
In the NAD molecules, you cut the 5' and the 3' for the whole chemical side.
Yeah, so what happens, I'm sorry, I didn't explain that well. If we go back to the diagram. Pop off the base, and we cut this phosphodiester bond over here. What we're going to end up with is a 5' end that has no base on it, and that's not what we get. It cuts here, and it cuts here. It cuts out the whole, it cuts out the sugar, and so you're still left with 5' phosphate end, and you're left with 3' hydroxyl because this whole thing gets cut out. So we'll end up with this thing being cut out, right, like this. The whole phosphate sugar, well, the base is gone, but phosphate and sugar get removed, and so we have a 3' end here and a 5' end here. Does that make sense? Otherwise, we have a sugar without a base sitting there, and that doesn't happen.
So is this also a restriction enzyme too?
Well, restriction enzymes cut here between the phosphate and the hydroxyl group. They cut here. That's what's happening here. It's cutting here, and then it's cutting again down here. So we get a hydroxyl group at this end and a phosphate at this end. So this enzyme is cutting twice. A restriction enzyme would cut the backbone just once between the phosphate and the hydroxyl. Okay? We all good? So again, you know, the advantage to putting on this adapter is that we only have to ligate in one molecule. We can put in a lot of that one molecule push the reaction towards both ends of our cDNA getting the adapters, because we need our cDNA at both ends to have the adapters. So these reactions, these ligations, we put in a lot of adapters. Think about the adapter itself. It's yellow and green, right? So I'll use green, but yellow I can't use. So I'm going to do green and red instead of green and yellow. Okay. So red is going to match the yellow in your diagram. So on our adapter, we have this, and then the blue. Okay. And then we're going to have that one nucleotide with the U. And I'll do that in blue just so it looks different. I'll stick the U there, so you know what's happening. And then the other side will be green. I'm not a great artist, so I'm doing the best I can here. And then we've got that single T overhang. And then this is going to be the step away in seconds. You can see it. This will be 5' end. This will be the 3' end. Okay, so our adapters, just floating free in solution, look like this. They have the 5' end paired with the 3' end of the primers. There's hydrogen bonds here, holding that stem together. This part doesn't match itself, and so there's no hybridization there, so it makes a loop. The U is here. This is our 3' end, and the 3' end has the T on it. Now, when you go to ligate these things to the double-stranded cDNA, we put in a lot of these. And our ratio, I forget the exact ratio, but I think it's something like 10 to 1. Well, that sounds pretty awful, because it sounds like at a ratio of 10 to 1, you could get a lot of adapter ligating on itself. But these adapters can't ligate together, because each adapter has a T overhang. And a T overhang doesn't hybridize to a T overhang, right? So in fact, the adapters cannot ligate together. And so because of that, we can put in a lot of adapters to force this reaction in the direction of getting an adapter on both ends of our cDNA. If cDNA only gets one adapter at one end and not at the other end, then it's not going to be as good as it. We have to get the adapters on both ends, so we put a lot of adapters in the reaction. Okay? Does that make sense? Okay. So it's pretty cool. Adapters can't ligate to each other. Our cDNAs can't ligate to each other. That's also really useful when we do this ligation. The cDNAs have single A overhang. Those can't ligate either. So this is really nice, because the only products that we should get out of this are adapters ligated to cDNAs. There's really nothing else possible in this case. And that's really a great way. If you can set up a ligation like this where nothing else can happen except what you want, that's pretty nice. So again, a really clever feature of this system. If we were to ligate on individual adapters to the side that were linear, we wouldn't have any of these advantages, would we? If we ligated linear adapter molecules, DMs, in different ligations, those adapters could ligate together because they'd be linear. cDNAs could ligate together. It'd be horrible. This is fantastic, right? cDNAs can't ligate together, our adapters can't ligate together. Amazing. Okay, good? All right, we're going to stop there, because that was amazing, and we're all pleased with how that